So this is a VLF instrument. It's one of the EM, electromagnetic series of instruments. This one's unusual in that it uses a distant transmitter, so the instrument itself only contains a receiver. And those distant transmitters are VLF, or very low frequency antennae, that are installed to basically to communicate with submarines underwater and things like that. So they operate over very, very long distances, and that means that more or less wherever we are in the world, we can pick up one of those antennae and use it as our signal. And what we actually aim to do with this, and I'm not going to turn it on for a reason that you'll find out a little bit later, is that we can measure two things. We can measure the tilt at which we need to hold the instrument, and that's measured using an eyepiece here, and it's calibrated in both degrees and in percent on the two sides of the calibration scale. And the other thing that we can measure is a quadrature that we measure by turning the dial here, and that's also a number given in percent. Okay, so it's got a plug-in that's tuned to a particular antennae, and we've got a couple of spares for different antennae if we need them for any reason. And we just make measurements along a simple profile at a spacing of something like a 1 meter or 2 meter, depending on how deep we need to go. So the way that we make the measurements on this is through sound. So it makes a really, really irritating whine that I'm going to have to inflict on you, but then that enables me to show how it works. So I'm going to switch it on now with power, and you can already hear that whine. Okay? So the way we start, and I'm going to turn the volume down a bit here, is we hold it horizontal, and then we swing it round until we find a minimum. Okay? That's very clearly the minimum in the sound, so that's the orientation in which we're going to use it. So now we switch it through 90 degrees, and then through a combination of altering the tilt and altering the quadrature, we aim to minimize that sound. And it's not very easy to do. You do get tuned in after a while, but that's probably about the minimum now. So that's 40 on the tilt and +5 on the quadrature. And then we just simply step along our meter or our carefully spaced distance, and then again we hold it in the same orientation and turn the numbers, turn the dial and alter the tilt till we get the best sound minimum. And that's not working particularly well. I'm not getting a good minimum here, but I would say that's probably 45 now and +15. Now the meter, same thing. Always keep it in the same orientation. We've already found that. And then tilting and altering the quadrature to get our best minimum. And again, I would say that's now about 35, and now we've gone to a small negative on the quadrature, -7. And I'm going to turn the power off so the irritating sound stops, and that's all there is to it. And you'll find in the textbooks, if you look, that there are standard types of signal that we get when we cross a steeply dipping conductor, and this is what the VLF is very good at finding. So it's good at finding a boundary between different rock types where there's a good contrast in conductivity. It can be used also for aquifer finding. So I'll show you the side here. This is where the dial is that we're reading through the eyepiece, and as I said before, this is the main part of the instrument itself, where you've got a volume a volume knob there and a quadrature knob there, and we take the cover off if we need to plug in one of the other antennae. It's also known as a Thor's hammer, this instrument, and it's been very, very widely used, particularly in mineral exploration, but for a small part also in environmental applications.